In this video, we are going to give a small introduction to random process and what is meant by characterization of a random process, which should help you to understand the forthcoming sessions with ease. Right. Before we go into random process, let us first check about what is meant by an experiment. An experiment is specified by a three tuple. It is specified by a three tuple. So when you specify this by a three tuple, what are the components? It is nothing but a sample space S and then your Borel function F, or rather to be very precise, the Borel field BF and your P. So here, to be more precise, S is countable, S is a countable or a non-countable set or an uncountable set representing the outcomes of the experiment. Representing the outcomes of the experiment. Your BF is the Borel field specifying the set of events for which consistent probabilities exist. For which consistent probabilities exist. And finally, P of dot or P is a probability measure is a probability measure that allows the calculation of the probability of all the elements in the Borel field. Of all the elements in the Borel field. So, if you recall, we had random variable, we used to write it as x. Then we introduced the time factor, we made it x of t, and then we want to talk about a random process, we will write it as x of t, comma s, that is your time and your state. And then now, when we define the experiment, we are going to define it by a three tuple S, which is countable or an uncountable set representing the outcome of the experiment. Then the Borel field specifying the set of events for which consistent probabilities are there. And then the probability measure P that allows calculation of the probability of all the elements in the Borel field. Okay. Next, we shall see what is a real random variable. A real random variable. So, what is this? A real random variable, let me denote it as x of eta, is a real valued function of sample space capital S, which is subject to the event is specified by how am I going to specify this event? The set of all eta such that my capital X of eta equal to x. And this is a member of our Borel field Bf for all x, guaranteeing the guaranteeing the existence of CDF. What is CDF? CDF is your cumulative distribution function. So how do we write this? We write it as eta, where x of eta equal to x. Okay. Next, what is the probability associated? So the probability of eta, you have x of eta equal to infinity, then this value is equal to 0, and it could also be probability of eta when x of eta is minus infinity, this is also equal to 0, or it could be both. Next, we go on to describe what is a random process. So we go on to describe what is a random process. So instead of assigning a real value to eta, a time function, let me say x of t comma eta is defined for each eta. Okay, then the random variable your x of eta is now called a random process x of t comma eta. Okay, so a random process is a family of time functions. Isn't it? Together, we also have a probability measure. So we need to be serious to mention it together with a probability measure. If you are to give a pictorial representation, you have eta from your sample space, which is now mapped on to your x of t comma eta. This would be a very simple way of expression of a wave form space. So here process is viewed here a process is viewed as a functional mapping, and is given as a map from eta to x of t comma eta, an ensemble of time waveforms. So it is an ensemble of time waveforms. At a particular time instant, t0, t1, etc., we get the value of the random variable to be just x of t0, x of t1, and so on. So now we are now got introduced to what is an experiment, what is a random variable, what is a random process, how can it be expressed in terms of a functional mapping. Next, we move on to classify this further into discrete time random process and continuous time random processes. When T is continuous, it is continuous time random process. For otherwise, it would be a discrete time random process. Fine. We shall now go further to just look into some more concepts based on what we saw previously. So let us note that at a particular time, at a particular time, let me say t equal to t naught, my random process x of t naught comma eta will specify a random variable since t is since t is a function of eta alone. That means eta belongs to your sample space. So this is one thing to be noted. Secondly, when both t and eta are fixed, then let me say my t equal to some theta naught and eta equal to some eta I, then my x of t naught comma eta I will now become a real number because both are fixed values. So real number for a real random process. It will become a real number for a real random process, or it would become a complex number for a complex process. Okay. Normally this x of t comma eta is denoted by just capital X of t, and the small x of t will denote a particular value of the random variable capital X. Okay. Here my x of t comma eta is called a sample function, or it is called a sample function or a realization of the process, or it is called a realization of the process. Okay, so it is important for us to understand the relationship between x of t comma eta, how the function behaves when t is constant, when both t and eta are constants, and to visualize it as a mapping. Right. Next, we move on to discrete time random processes. So, what is a discrete time random process? Okay. So, idea is to find out little more on this. If the indexing set, let me call it as gamma. So, if the indexing set, say gamma, can be put into one-to-one correspondence, can be put into a one-to-one correspondence. See, now you see why we want to express it as a map. So one-to-one correspondence can be established very easily if we are able to look into it as a mapping, as a one-to-one correspondence with the set of integers, with the set of integers. The random process is called the random process is called a random sequence. It is called a random sequence. So this is the next thing that we have learnt. What is meant by a random sequence, or in other words, a discrete time random process. Okay, so it is known as a random sequence or a discrete time random process. Next, we move on to characterizations of a random process. So, characterizations of a random process. I denote it as RP. Okay, so now we know what is a random process. We also know what is discrete time random process. We are able to visualize. We are able to visualize it as a function. So now we look into the characterizations of the random process. The partial characterizations of a random variable, the partial characterizations of a random variable will include number one, your mean, number two, your variance, then moments, and the like. Number three, moments, to mention a few, and the like, etc. Okay. Now, all these are functions of time. This is important. All these are functions of time. So time plays a very crucial role in the characterization of a random process. For a random process, for a random process, nth order densities, nth order densities, autocorrelation function, autocorrelation function, and spectral density will be defined, and this will be very useful to analyze the process. So this may be pictorially represented stage-wise by the hierarchical relationships between the characterization of the random process. At the topmost level, we have the total characterization. From 1, below that comes the partial characterization. From the total characterization, we are led to the nth order densities. From the nth order densities, we move on to the autocorrelation function. Now, from autocorrelation function, that is represented as 2.1, we can still go down to find the power spectral density. The power spectral density is got by taking the Fourier transform of the autocorrelation function, and by taking the inverse Fourier transform, we may revert the relation. Now, from 2, we also move on to 2.2, which is nothing but the higher order moments, and from the higher order moments, we can move back and forth to the higher order spectrum. From the second level, that is the nth order density, we move down to get into the first order densities. Now, what are the contributing factors here? The first order densities are your mean, your variance, and then the higher order moments, which we will be finding in the next step. So this pictorial representation will give you the hierarchical relationship between the characterizations of the random process. Okay, so I suppose now you are getting an idea of what is an experiment, a random variable, a random process, and then how we go about characterization of the random process and the step-by-step relationship between the characterizations of your random process. Now, the next thing what we would like to discuss is the total characterization of a random process. Total characterization of a random process. Alright, so under total characterization, how many characterizations are there? There are countably infinite or infinite number of random variables described for a random process. So, it is as therefore we say that the random process is defined to be completely or totally characterized. A random process is completely or totally characterized if the joint densities of the process, if the joint densities, for the random variables specifically, for the random variables, let me call it like x of t1, x of t2, etc., are known for all times tn and also for all n then we say that it is the random process is totally characterized. Right. Next, what do we understand by first order densities of a random process? What do we understand by first order densities of a random process? Okay. If the first order probability density function, if the first order probability density function defined generally by fx of x, that is, this is the notation used, or the notation could be f of x comma t. If they are all the same and if they do not depend on t, if they do not depend on t, this is important. If they do not depend on t, then f of x comma t is called first order density of the process, is called the first order density of the process. Suppose it depends on t, that is, otherwise we will have a family of first order densities because you will have f of xt1, f of xt2 and so on. So otherwise we have a family of first order densities. Okay, right. Next, the first order densities are only partial characterization. So they will not contain much information that specifies the joint density of the random variable. So we have to find the joint densities of the random variables which is defined at two or more different times. That is also important. Next, we move on to mean. mean of a random process. Okay, so what is meant by mean of a random process? The first order density function of the random process, which I denote by f of x comma t, gives the PDF of the random variable. This gives my probability density function of the random variables xt defined for all time. Okay, it is defined for all time. Hence, my mean equal to eta x of t equal to my e of x of t, which is nothing but integral minus infinity to infinity x ft of x into dxt. Okay, derivative of the random variable xt. Note, eta x of t, your eta x of t is a constant. Okay, this looks very cumbersome. Let me rewrite this. This is dxt. Next, what is meant by variance of a random variable? Variance of a random variable. Variance of a random variable is sigma x squared. Now we will look into variance of a random process. So how do I denote this? Variance of a random process. This is given by my sigma x, the time parameter counts. So this is nothing but e of my xt squared minus eta x squared x of t. This comes from the formula. What formula? Your usual variance formula. Okay. So when I say variance, it should be sigma square. Knowing mean and variance along with Chebyshev's inequality, one can clearly interpret the region of space where the sample function from the process will most likely lie. So this is very important to us. So with this, we move on to second order density of a random process. From this, we move on to second order densities of a random process. Right. We are moving to second order densities of a random process. So we consider two time instants, say T1 and T2. The corresponding random processes x of t1 and x of t2. The second order densities are a family of densities specified for t1 not equal to t2 and are denoted by f of x1 comma x2, or they may also be denoted by x1 comma x2 colon t1 comma t2. Okay, generally they are not independent, so it cannot be determined from just the first order density function. Right, now under this we would like to see a glimpse of autocorrelation formulas for your autocorrelation function. So some notable formulas which we would like to see. One is your autocorrelation function of a real process. The autocorrelation function of a real process is two-dimensional, and we have our Rxx is not P, R, Rxx of T1 comma T2 is expectation x of T1 into x of T2. Right. Okay. This function is an even function. If we have to delve deep into properties, it has got some significant 4 to 5 properties. Next, we find out auto covariance. Auto covariance function. what is meant by an autocovariance function? This is Cxx of T1, T2, and this is nothing but autocorrelation of T1, T2 minus the mean eta x at T1 into product with eta x at T2. Next, normalized autocovariance. Normalized autocovariance function. Okay, what is normalized autocovariance function? This is denoted by rho xx of T1, T2, which is nothing but our Cxx of T1, T2 divided by square root of, I will have Cxx at the same point T1, T1 into Cxx at point T2, T2. Okay, so this is the function. After this, we have just looked into all real random processes. Similarly, we also have complex random processes for which here our Cxx, that is autocovariance, would be the autocorrelation function minus eta x of T1 into the conjugate eta x star of T2. And the normalized autocovariance function in the complex case would be rho xx of T1, T2 equal to Cxx of T1, T2 divided by Cxx of T1, T1 into the conjugate Cxx star of T2, T2 under the square root. Okay. Next, we will just have a look at the power spectral density. The power spectral density is got from the autocorrelation function. Your power spectral density is got from the autocorrelation function. And how does it get to this power spectral density? We take the Fourier transform of the autocorrelation function. That is your PST. Okay, this describes the region where in the frequency domain the power of the process exists and also the relative proportion of the power at each frequency exists. Okay, the properties of power spectral densities are also notable. Thank you. After this, we move on to stationary random process and wide sense stationary random process. Before that, we need to know what is meant by stationarity. So let us look into what is meant by stationarity of a random process. Okay, so we will look into this. What is meant by stationarity of a random process? A random process is said to be strong sense or is said to be strong or strict sense stationary. Okay, if the set of random variables, let me say x of t1, x of t2, etc., x of tn, and x of t1 plus t, comma, x of t2 plus t, comma, etc., x of tn plus t have same PDF, have the same PDF for all t. If this is the case, then we say that the stationarity is strict sense stationary. That is, the process is a strict sense stationary process, or it is said to be a triple S process. Okay. Next, what is meant by wide sense stationary random process? Wide sense stationary random process. So what is meant by wide sense stationary? We represented this as a WSS process. A process x of t is weak sense. A process x of t is a weak sense or wide sense stationary if number one, the expected value of the process E of x of t is a constant, and number two, the autocorrelation function Rxx of, let me say, 2 time instant t1 comma t2 is equal to Rxx of tau, where tau is the modulus of the difference of the time interval t1 minus t2. This, if it satisfies these two conditions, then it is said to be wide sense stationary. Also, the process, if it satisfies two, okay, we say it is stationary in autocorrelation. We say it is stationary in autocorrelation. If it satisfies one, we say it is stationary in mean. Okay, next. A random process is called asymptotically stationary of a particular sense of conditions. What is meant by this? Asymptotically stationary. This word you will find everywhere. Asymptotically. So, what is asymptotically stationary? A process is said to be asymptotically stationary of a particular sense of conditions for that sense if, see, it is said to be asymptotically stationary if of a particular sense if the conditions of that sense if the conditions of that sense are satisfied in the limit are satisfied in the limit as uh, in the limit they are satisfied in the limit as times approach or as times become infinite. In this case, we say that they are asymptotically stationary. Some processes are in a sense stationary or for particular time variables. Okay. Next, what is meant by cycle stationary? What is meant by cycle stationary? This a process is said to be cycle stationary of a particular sense if the sense is satisfied if the sense is satisfied for times that are periodically displaced, for times that are periodically displaced, say, by an amount capital T. So now we have also known what is strict sense stationary, what is weak sense stationary, what is meant by asymptotically stationary and cycle stationary. So in this long lecture of around 40 minutes, we have had an in-depth introduction to random processes, starting from the definition of an experiment, landing up to stationarity of processes. Thank you.